Welcome, ladies and gentlemen. This is our third video on intermolecular forces of attraction. And in this video, our focus is going to be on phase changes with intermolecular forces of attraction, and with a specific focus on heating and cooling curves. And again, our goal here is to talk about what's happening with intermolecular forces of attraction during phase changes, to interpret the heating and cooling curves, and do some calculations from heating and cooling curves. So the first thing to discuss is about phase changes with IMFs. And there are certain phase changes if we're melting or if we're boiling. Basically, if we're going from a solid to a liquid to a gas, we are breaking IMFs, versus if we are going in the opposite direction. If we're going from a gas to a liquid to a solid, if we're condensing or freezing, then we are forming IMFs. Basically, are your molecules becoming more spread apart, or are your molecules coming together? But there are energetics that go along with both of those. And so the big thing to talk about if we are melting or boiling is you're not actually breaking apart the molecule, meaning the molecule itself is staying intact. So we are not breaking any chemical bonds. We always want to be very careful with our word choice when we're talking about IMFs. We are not breaking bonds. When you boil water, you are not breaking the bonds in water. But what you are breaking the attraction between the water molecules. So because you are breaking that attraction, energy is absorbed. It requires energy to separate the water molecules, meaning that process is absolutely endothermic. You are trying to pull apart molecules when there's an attraction that will require some energy. On the other hand, if we are condensing or freezing and we are bringing our molecules closer together and we are forming intermolecular forces of attraction, you are making the molecules more stable. You are making the set of the molecules together more stable. They're forming attractions with one another. That is an exothermic process. That is releasing energy. A solid is at a lower energy than a gas is. So if we're going from a gas to a liquid to a solid, the gas has to get rid of some excess energy. I sort of think of it like a gas is too highly energetic to become a liquid. So in order for the gas to become a liquid, the gas has to shed some of its energy. And that's exothermic. That's losing energy. That's an exothermic process. Names of phase changes, just to go over them just to go over all of them so that we know the ones like going from a liquid to a gas, that's boiling, and going from a gas to a liquid, that's condensing. Likewise, you should already know that going from a solid to a liquid is melting. We sometimes call that fusion. And going from a liquid to a solid, that's freezing. We can also call that crystallization or solidification. But we also need to make sure that we know the other ones, going from a solid to a gas directly. So this arrow right here, that's sublimation. That's where we are completely bypassing the liquid phase of matter, and we're going directly from the solid to a gas. Now, the opposite of sublimation, so this arrow over here, that's called deposition. So that's going directly from a gas to a solid, completely bypassing the liquid phase of matter. Now, with these sets of phase changes, right here, these are where we are breaking IMFs. All of them. So these are our sets where the molecule stays intact, but we're splitting the intermolecular forces of attraction. We're pulling the molecules apart. So these are your endothermic phase changes, your ones that require energy, versus these sets of phase changes. Right? These are where you are forming IMFs. So these are your exothermic phase changes, the phase changes that actually release energy. Now, with specifically looking at melting and boiling, there are some calculations that we can do with that. Heat of fusion, delta HF, is the enthalpy change associated with melting a solid. So fusion is another term for melting in this context. And we can do some calculations with that, because the unit for heat of fusion is very, very typically in joules per mole or kilojoules per mole. So this formula right here, which is not on your reference table, but really all you need to kind of know is that, well, if this is the unit, then that tells you everything you need. If you multiply the number of moles by kilojoules per mole, well, moles will wind up canceling and you'll determine the amount of heat needed to melt a particular sample of a substance. Likewise, heat of vaporization, delta HV, is the enthalpy change associated with vaporizing or boiling a liquid. And exactly like delta HF, our units are typically joules per mole or kilojoules per mole. So now we're just multiplying the number of moles by the heat of vaporization in order to find the heat required to boil a sample of a substance. Now, delta HF and delta HV, they're actually very similar to specific heat in that they are a constant. They're different for every single substance. There's something that you could look up about a substance. And they have a direct commentary basically on the strength of the intermolecular forces of attraction, meaning the more energy is needed to separate a substance, and let's say when you're melting it, that the stronger the intermolecular forces of attraction, the larger the heat of fusion for that substance. Now, this thing over here, generally speaking, delta delta HV is always larger than delta HF, meaning it's always going to take more energy to vaporize a substance than it is to melt a substance. Because when you are vaporizing a substance, you're turning it from the liquid phase to the gaseous phase. You are separating all of the intermolecular forces of attraction, all of them. You're pulling your molecules completely apart. Versus when you are melting something, you're going from a solid to a liquid, well, there's still tons of IMFs in a liquid. There's just slightly less IMFs in a liquid than there is in a solid. So when you're melting something, you're breaking some of the IMFs, but when you boil it, you're breaking all of the IMFs. So we expect for everything across the board that its heat of vaporization is going to be significantly larger than its heat of fusion based on the amount of IMFs that we're breaking in these two cases. All right, so heating curves. Hopefully this is going to be a bit of a review for you because I know that this was covered very thoroughly in previous science classes. So a heating curve is simply showing, it shows time on the x-axis and temperature on the y-axis, and it shows how the temperature of a substance changes as it undergoes the phase changes. So a big point here is that phase changes occur at one temperature and one temperature only, meaning this right here, that's a phase change. Notice that the temperature is not changing. This right here, that's a phase change. Again, the temperature is not changing, right? Boiling point, melting point, not a range of temperatures, but a single temperature. And if we start here, we have the solid, and then when we melt, we have the solid and the liquid together. So you have both phases present during a phase change, and then we have the liquid, and the liquid is increasing in temperature, and then we have the liquid and the vapor in equilibrium, right? This is the boiling, this is melting, and then we have the vapor, and then we simply heat it up. Now, this is the process right here. This is where we're breaking IMFs. The boiling process. During the melting process, we are also breaking IMFs. So we can also look at what's happening during these parts of the curve where we are not necessarily breaking IMFs, but instead just heating up the substance. This is where we are increasing the kinetic energy of the system. If you remember from gases, that kinetic energy is directly related to temperature. Temperature is a measure of the average kinetic energy in a system. So if we are increasing the temperature of a substance, then we're increasing the kinetic energy. Now, during the phase changes where we are not increasing the temperature of a substance, that means that the kinetic energy is staying the same. But we have to be increasing the energy of the substance because we are breaking its IMFs. It's absorbing energy. So during these phase changes, we are increasing the potential energy of the system. Right, the molecules themselves are not moving any faster, but we are pulling them apart from one another. So the system is absorbing energy. It's just a different type of energy. Now, doing calculations from a heating curve, basically requires breaking your information down into specific line segments. Each section of a heating curve has its own type of calculation. It has its own heat calculation. Now, we would do Q equals mc delta T for all the sections of a heating curve where your temperature is actually changing, right? Delta T, so changing temperature. So we're using Q equals mc delta T, which we've seen before. But during the sections of the heating curve where we're not changing temperature, then we have to use our Q equals NHF or Q equals NHV for the melting and the vaporizing. If you simply do Q equals mc delta T for your final temperature versus your initial temperature, you're completely ignoring the phase change that's occurring and all the energy that's going to be required to do that. So you can't just do one enormous Q equals mc delta T for basically the start of a heating curve to the end of a heating curve. You have to break it up into the individual segments and do a calculation for each line segments. Then all you need to do at the end is add your Q values together. Just add them, and that's going to give you the total amount of energy needed to move from one point to the next. So the final thing that we're going to do in this is just a sample calculation. What do I mean by that? Well, we could have this question that says how much energy is required to raise the temperature of a 10 gram ice cube from -5 degrees Celsius to 75 degrees Celsius. If you do just Q equals mc delta T for this, saying, okay, well, the initial temperature is -5, the final temperature is at 75, I'll just do Q equals mc delta T for an 80-degree temperature difference, you're completely ignoring the fact that we have a phase change at 0. And you're not taking into account the energy that's required to undergo that phase change, so just you're wrong. Like, no, you can't do that. So I'm actually going to start by just sketching a heating curve for the information that we have, meaning we know that we're starting at -5 degrees Celsius, so I'm going to label that -5 degrees Celsius. But I also know that the ice cube is going to melt at 0 degrees Celsius, which is why I drew this flat line here. And I also know that it's going to end at 75. So I know that I'm going to have the solid here, then the solid's going to melt, and then I'm going to have the liquid, and I'm going to be heating it up here. If I want to calculate the amount of heat needed to do this, I have to break this up into the 3 line segments that it has, A, B, B, C, and C, D, and there's a different calculation for each. So for A, B, because the temperature is increasing from -5 to 0, I'm doing a Q equals mc delta T calculation. But during BC, because I'm melting and I'm not changing the temperature, this is where I'm going to do Q equals NHF. F because it's melting, and melting is fusion. And then during CD, because again I'm increasing the temperature of the liquid, I'm going to once again do Q equals mc delta T. But you have to be very, very, very careful here, because our constants are different, meaning the specific heat of liquid water is not the same as the specific heat of solid water. So the C that I'm using here, this is the specific heat of ice, versus the C that I'm using here, this is the specific heat of liquid water. And I can't use the same C. So doing this math, we're just going to do 3 Q calculations for these 3 different line segments. So AB is Q equals mc delta T, and we know that we have a 10 gram sample. Now I'm going to use the specific heat of ice here because at AB I have solid water, not liquid water, so that's 2.09 joules per gram Kelvin times the change in temperature, which is a change of 5 degrees Celsius, which is also a change of 5 Kelvin, because it's about the difference. It's not the absolute temperatures, it's just how much the temperature changed by. So I know my delta T is 5 Kelvin. And then you just do that math, and you get a Q value of 104.5 joules. So 104.5 joules is required to go from point A to point B in the cooling curve. BC, this is where we're melting it, so I'm going to do Q equals NHF. Now I'm doing Q equals NHF, moles times HF rather than grams times HF, because that's the unit that I have for delta HF. I have kilojoules per mole, not kilojoules per gram. So I am going to have to do a little bit of math here. So I have my mass of my water, but I know that I can turn that to moles through gram formula mass. So I'm just going to even set up the t-chart just right in my equation to get my moles of water, and then multiply that by the 6.01 kilojoules per mole, and I get a Q value, the energy needed to melt, of 3.34 kilojoules. And then I have to erase some stuff because this is a multi-step process. And then I'm just going to do my last line segment, which is CD, which was a changing temperature, and this is Q equals MC delta T. Now this was for the liquids, so now I'm going to go back to using 4.18 joules per gram Kelvin, again times the change in temperature, which is 75 degrees Celsius, which also is a change in temperature of 75 Kelvin. If you're not convinced of that, then turn 0 degrees Celsius into Kelvin and 75 degrees Celsius into Kelvin, and then subtract them. And hopefully by then you'll be convinced that you get the same value. And so for line segment CD, we get a value, a Q value of 3,135 joules. And then you simply have to add your Q values together to get the total amount of heat needed to take that ice cube from -5 to 75 degrees Celsius. However, this one's in joules, this one's in joules, this is in kilojoules, so you cannot simply add them as is. So I'm going to convert them all to kilojoules because otherwise I think I have an awkward number. So it's just going to be the 0.1045 kilojoules plus 3.34 kilojoules plus 3.135 kilojoules gives the total amount of energy needed to take this ice cube from -5 to 75 degrees Celsius, 6.76 kilojoules, and that's your final answer. So the big point is that if you have, if you're doing a calculation from this heating curve, you have to take into account the different line segments, and you're doing a different calculation for each one, and then simply summing them all together.